Before we can get into plate tectonics, we have to talk about what makes up the plates, which is our lithosphere. But in this video, we're going to talk about the lithosphere and the asthenosphere, the layer that lies below it inside of the Earth. So remember from our last video that we didn't really know anything about plate tectonics until the 1960s. That's because in the Second World War, we started using submarines, and we really quickly realized that we didn't know anything about our oceans and how deep they were and the different features we found along the seafloor. So as we were exploring our oceans, we discovered this oceanic ridge system. In the middle of all of our oceans, we have this kind of linear mountain range cutting through the middle of them. They also found really deep areas of our oceans called trenches, and that there were earthquakes associated with these areas. During this time, they also figured out how to radiometrically date rocks, which is something we'll get into probably about a month from now. But they realized as they were dating the ocean's crust that they couldn't find any crust anywhere on the Earth that was older than 180 million years old. And this sounds like a lot, but remember, the Earth is 4.5 billion years old. So the fact that we're only finding oceanic crust that's up to 180 million years old, we're missing a lot of oceanic crust. So a lot of this new information that we're gaining led to this theory of plate tectonics. Before, we talked about the hypothesis of continental drift. And I just want to take a second here and talk about the difference between a hypothesis and a theory. A hypothesis is just an idea. It's something that you might have tested a couple of times to see if it was right or wrong. A theory is something that's been tested by hundreds of different people, hundreds of different times, and every single time the results line up. So gravity is a theory. It's something that's well regarded and accepted. So now that we're exploring our oceans, we've been able to take Wegener's hypothesis, his idea, and with so many different experiments all leading to the same results, it's expanded to what we call a theory. And this is the theory of plate tectonics. It's a lot more encompassing than that hypothesis of continental drift because it has tons of different experiments by hundreds of people in hundreds of different locations. But back to the layers that make up plate tectonics. We're going to see that the outermost layers of our planet, we typically think of them as crust, mantle, and core. But when we're talking about plate tectonics, we don't want to divide the Earth into these three layers. Instead, we're going to have two new layers that we're going to think about. And these are called the lithosphere and the asthenosphere. The lithosphere is going to be the outermost layer where we live. It's going to be all of the crust where we have that solid rock, and then it's going to have the uppermost, coldest region of our mantle as well. Beneath this solid lithosphere, we're going to have our more liquid and flowing asthenosphere, which we'll talk about on the next slide. But when we're looking at our lithosphere, again, that outermost portion of all of the crust and a little bit of the upper mantle, here we're going to see that it's very different beneath our oceans and beneath our continents. So our oceanic lithosphere is going to be a lot thinner. It's going to be up to about 100 kilometers or 60 miles thick. The reason it is going to be so thin in comparison to the continents is because it's made out of mafic rocks. Remember, those are the ones that are darker in color and really dense because they have so many metals inside of them. Because they're so dense, these are going to be the ones that want to subduct or go back inside of the Earth. And this will become important throughout this chapter. But we're going to see that the second type of lithosphere is our continental lithosphere. And it's going to be the exact opposite of our oceanic lithosphere. And that's because our continental lithosphere is going to be twice as thick. And that's because it's felsic rocks. Remember, those are light in color, they're lightweight with low density, because they're made out of those salty elements. Because the continents are so thick and not very dense, they're going to be able to float on top of the magma beneath them. So our continents will never subduct. It'll always be that thinner but denser oceanic lithosphere. But beneath that solid lithosphere, we have our asthenosphere. Because this layer is closer to Earth's core, it's going to be hotter. And because it's hotter, the material there is going to be weaker. And it's going to be able to flow. But it's not flowing just like a river. It's going to be flowing incredibly slowly. So think about pouring like molasses or really thick honey out of a bottle. It pours out, but it's going to take a while because it flows very slowly. But our asthenosphere, the rest of our upper mantle, is going to move independently from the lithosphere, or the layer above it. But if we're just looking at the lithosphere, the outermost layer, we're going to see that it's broken up into irregular pieces that all fit together. And overall, we have about 7 major lithospheric plates on our planet. And these plates can either be under the ocean, like the Pacific Plate, or it could be underneath a continent, like the South American Plate. We'll see that the lithosphere, how it moves, a lot of the times is going to be determined on what kind of plate it sits on. Remember, oceanic lithosphere is thinner, denser, and likes to subduct or sink back into the earth. Whereas continental lithosphere is thicker and buoyant. It's going to want to float. When we're looking at all of the different plates that make up the lithosphere, we're going to see that they interact with each other in 3 general ways. The first is going to be what we call a divergent boundary. Here, the 2 plates are moving away from each other. When this happens, we're going to have magma coming up between the 2 separating plates and create new seafloor. Because it's creating new seafloor, we call divergent boundaries constructive margins, because it's constructing new seafloor between them. Our second general type is called a convergent boundary. This is where 2 plates are converging or moving towards each other. And depending on the type of plates that are colliding, we're either going to have subduction, where one will be pushed back into the earth, or we'll have mountain building. And our third type of plate movement are called transform plate boundaries. Here, they're neither moving towards nor away from each other. They're simply sliding side by side. And we're going to get into each of these 3 in more detail in the next video.